Welcome to This Explainer. Today, we're diving straight into how Sri Lanka's absolutely vital fishery sector managed to survive an unprecedented series of shocks, and how data science is literally building its future resilience. You see, this sector is a lifeline for 500,000 people, providing crucial jobs and food security. But recently, it was put to the ultimate stress test. We're going to look closely at some incredible deep dive research from the University of Moratuwa that takes all that chaos and translates it into actionable data.
Here's our roadmap for today. We'll quickly cover the perfect storm of crises, contrast the marine and inland systems, look at delayed climate effects, measure the actual disruptions, forecast future prices, and finally wrap up with building sector resilience.
Part 1. The Perfect Storm, a Timeline of Crises.
Just look at this timeline between 2019 and 2025. It illustrates the sheer scale of the chaos Sri Lanka's fisheries faced. First, the tragic 2019 Easter Sunday attacks, followed rapidly by multiple waves of COVID-19 lockdowns. And then, right as the dust was settling, the massive 2022 fuel and foreign exchange crisis hit, effectively stranding boats and keeping them from going to sea. After that, severe southwest monsoon floods in 2024. Any single one of these events is disastrous, right? But stacked together like this, it's a true perfect storm.
Moving to Part 2. Marine versus inland fisheries, contrasting ecosystems.
So to really grasp how these crises hit the sector, we've got to break down the two totally different systems running in Sri Lanka. It's absolutely crucial to understand that oceanic fleets and inland aquaculture behave completely differently when stressed. On one side, you've got marine fisheries. These are your offshore deep-sea fleets and nearshore coastal fishing. They are highly exposed to monsoonal winds and ocean temperatures. But on the flip side, you have inland fisheries, which is your reservoir capture, aquaculture, and shrimp farms. These are driven by inland ambient temperatures and the rainfall that recharges the reservoirs.
Let's really unpack the data here, using STL decomposition, which splits production into the overall trend, the seasonal changes, and just the random noise. Now, look at the left side first. Check out that green trend line for marine production. That is a worrying, steady decline from 35,000 metric tons in 2019 down to 23,000 by 2022. And that gray residual line at the bottom, that highlights the chaos, massive, unpredictable swings from external shocks. But then contrast that with inland production on the right. Its green trend line is way more stable. And crucially, look at the red panel there. Inland systems have these incredibly strong, predictable seasonal peaks driven by monsoon-induced reservoir filling from July to September. It's just vastly more controlled.
Okay, Part 3. Climate and delayed effects, tracking the weather.
Before we dive into the next chart, let's quickly define lag correlation. Simply put, it's a way of measuring how today's weather changes how many fish you catch next month or even the month after that. A zero lag means an immediate effect. A 1-month lag means we're looking at how last month's weather is affecting this month's catch. The researchers used a statistical tool called Spearman's Rho to calculate all of this.
All right, let's thoroughly examine this heat map, because it's fascinating. When we map these delayed effects, the blue boxes indicate a negative correlation, meaning a decrease in fish, while red indicates a positive boost in production. Look at the marine temperature row right there. At lag 1, we see a highly significant negative 0.418. That means a warm ocean today suppresses the marine catch 1 month later. But now drop down to the bottom row for inland temperature. It's the exact opposite. The boxes get progressively redder, peaking at a strongly significant positive 0.368 at lag 3. So warmer preceding inland temperatures actually boost production 2 to 3 months later, really aiding aquaculture growth. Finding these opposing lag structures is a massive discovery.
Part 4. Measuring the disruptions, quantifying the shocks. Looking at these average seasonal prices, the market's stress points are just glaringly obvious. Notice that intense dark red clustering right in the middle of the year for the offshore category, across both retail and wholesale. Retail prices were hitting over 2,000 rupees per kilo in June and July. These pronounced mid-year peaks align perfectly with monsoon supply constraints, when rough seas literally ground the fleets. Meanwhile, check out the pale yellow row for the inland category. Prices there stay incredibly stable all year round.
Now, tracking price volatility, or the coefficient of variation, reveals immense market chaos year over year. Notice how the retail volatility in the top graph fluctuates way more wildly than the wholesale volatility on the bottom. If you track that vertical line for 2022, you'll see every single retail category, coastal, offshore, shrimp, inland, spiking upwards simultaneously. That economic crisis created a massive wave of instability across the entire food supply chain.
And that brings us to a really fascinating subplot in the data. The researchers pointed out that, quote, the 2022 fuel and economic crisis led to a sharp decline in marine production while inland production rose to its highest level. Basically, this implies a natural substitution effect. One system actually compensated for the collapse of the other. Let's look at the visual proof of this.
When we overlay those historical disruptions directly onto the production data, that substitution effect is undeniable. Track the 2022 fuel crisis marked by that solid purple band. You can see the blue marine line plunging downward right into the heart of that crisis. But look closely at the red inland line during that exact same time window. It shoots straight up, forming the highest peak on the entire chart. When the marine fleets literally couldn't get fuel, inland production spiked to fill the food gap.
Now, to isolate the exact mathematical impact of those specific shaded events, data scientists use a technique called an interrupted time series, or ITS. Think of it as a quasi-experimental method that calculates precisely how much a sudden shock shifts either the flat level of production or the angle of its trend line, compared to how things were going before the shock hit. Let's really look at these ITS graphs because they mathematically prove exactly how each crisis shifted production. The blue dots represent the pre-event window, moving into the orange event window, and then the green post-event window. Look at the COVID-19 Wave 1 lockdown graph. Marine production basically fell off a cliff, dropping dramatically from its pre-event baseline. A similarly devastating step-down happened during the fuel crisis. But check out the top right graph. During that same fuel crisis, total inland production steps up into the orange phase and actually continues climbing.
And the actual numbers extracted from this analysis? They are staggering. Look at this table. During the first COVID wave, marine production suffered an immediate 15,474 metric ton loss. Interestingly, during the 2021 monsoon floods, marine production initially jumped by about 22,000 metric tons, likely due to nutrient runoff feeding the fish. But the trend after that turned sharply negative. The January 2024 inland floods caused a similar massive initial surge of 13,000 metric tons, which was then followed by a steep collapse.
Which brings us to Part 5, forecasting future fish prices using the SARIMAX solution.
So, what's the big takeaway? How do we use all this historical data, climate tracking, and shock analysis to actually protect the food supply moving forward? The answer is predictive forecasting. By using an advanced statistical model called SARIMAX, which for the data nerds out there stands for Seasonal Autoregressive Integrated Moving Average with Exogenous Factors, researchers improved inland production prediction accuracy by almost 50% compared to basic seasonal models.
As this table clearly shows, SARIMAX consistently beats out basic seasonal baselines across the board. Why? Because it accounts for trends, seasonality, and crucially, those lagged climate effects like temperature and rainfall we talked about earlier. The results are just incredible. Not only did it reduce production errors by nearly 50%, but it reduced inland retail price prediction errors by almost 64% and shrimp farms retail price errors by a massive 66%.
Looking at this bar chart for average forecast errors, the dramatic drop is undeniable. See the basic seasonal naive model on the right? That model just assumes this week will look like last month, and you can see it has massive error rates. But look at the SARIMAX results on the left. Both error bars are slashed essentially in half. By feeding climate and historical shock data into SARIMAX, it acts almost like a highly accurate weather app, but for predicting market fluctuations before they hit the consumer. Finally, Part 6. Building sector resilience, actionable takeaways.
Because, let's be real, data is only useful if it leads to action. Policymakers now have specific insights to actively manage risks. Fishermen can use these SARIMAX forecasts for sell versus store decisions, knowing exactly when to put their catch into cold storage because they can foresee a price dip coming. However, the researchers are quick to warn that these should be used as decision support tools, not blind autonomous triggers. Planners can use the historical volatility data to prioritize building cold storage infrastructure in highly volatile districts, and when the next major shock inevitably hits, the government can use those ITS models to anticipate exactly how many weeks a recovery will take.
We've seen today how translating absolute chaos into structured data builds true resilience. Sri Lanka's fisheries literally survived terror attacks, a pandemic, economic collapse, and climate disasters. And now, they actually have a predictive framework to face whatever comes next. Which leaves us with one critical question. If this level of rigorous data science can forecast and protect the survival of Sri Lanka's fisheries, what other fragile global food systems could we protect next? Think about the possibilities. Thank you so much for joining me on this explainer. Until next time, stay curious.